Dr. Shogo Kumagai-san from the Tohoku University. He is an assistant professor at Tohoku University in the Graduate School of Environmental Studies. And he's also editor of the Journal of Analytical and Applied Pyrolysis since 2018. He was a research fellow at the Japan Society for the Promotion of Science, JSPS. His research work mainly involved the development of pyrolysis process for recovering valuable feedstock from plastic, biomass, fossil, and their mixtures. And also is involved in the development of chemical and mechanical recycling process for waste plastics. He has published 91 papers in peer-reviewed journals, and he also contributed to 19 book chapters. He has 2 patents, and he's been invited in a number of conferences and received 21 awards. I can see his extensive profile, and with reference to the pyrolysis, I'm sure you find his presentation useful to you. He is going to make a presentation on the characterization of engineered plastics using pyrolysis under helium, air, and UV. Dr. Shogo-san, now it's your turn. Let me invite you to share your screen. Please open your webcam as well. Yes, you did already.
Thank you. Thank you very much for your kind introduction.
Okay, there you go.
Okay.
Share your screen.
So can you see my full screen? Okay.
Yes, please.
Okay, thank you. Okay, so thank you very much for your kind introduction. So I appreciate this great opportunity to talk in this webinar. So currently I'm working in a recycling chemistry laboratory in Tohoku University, and the recycling chemistry laboratory is managed by Professor Toshiaki Yoshioka. And in his laboratory, I'm researching development of feedstock recycling technologies for waste plastics and biomass, so which includes simple pyrolysis, co-pyrolysis, and catalytic pyrolysis approaches. In addition, I also belong to innovative analytical pyrolysis laboratory, so which is actually endowed laboratory established by Frontier Laboratories. So as Dr. Kartik has already mentioned, the Frontier Laboratory has developed analytical pyrolysis instruments and methods, and has manufactured very famous micro-furnace pyrolyzers. And in this laboratory, I'm working on development of a new analytical pyrolysis techniques using micro-furnace pyrolyzer gas chromatograph system. So today, I want to talk about my recent works in employing pyrolyzer gas chromatograph systems for characterizing engineered plastics under helium, air, and UV. So let me briefly start talking about pyrolysis and pyrolysis gas chromatography. So Dr. Kartik has already mentioned that pyrolysis involves the decomposition of polymeric materials, so which have low solubility, high molecular mass, and low volatility. So pyrolysis of polymeric materials produces smaller molecules by the application of heat alone in an inert atmosphere. So in the case of lignocellulosic biomass, pyrolysis of it produces gases such as carbon monoxide, carbon dioxide, methane, etc., and liquids such as anhydrous sugars, frans, and oxygen-containing C2, C3 molecules, and C2, C3 compounds from cellulose and hemicellulose, and methoxyphenols from lignin unit. So most of the pyrolysis researches are roughly categorized into applied pyrolysis and analytical pyrolysis. So applied pyrolysis involves the development of pyrolytic processes for producing variable chemicals, energy carriers, and materials from fossils, renewable feedstock or waste, along with the recycling of materials and the disposal of toxic substances. So on the other hand, analytical pyrolysis enables elucidation of chemical composition and structure of materials in the wide field involving the use of new instrumentation and new analytical methods based on pyrolysis reactions. So I guess that many of you in this webinar are working in the analytical pyrolysis field. So pyrolysis gas chromatography allows pyrolysis of polymeric materials in a micropyrolyzer, followed by GC analysis of the pyrrolidate. The necessary sample amount is microgram to milligrams, and capillary columns and mass spectrometer have been commonly employed for PYGC, whereas the detection system should be selected to suit the purpose of pyrrolidate analysis. So this image shows the micro furnace type PYGCMS system. So you can directly put a solid, liquid, and gas sample in the furnace. And then if you want to conduct pyrolysis with a slow heating rate, the sample holder should be set in the furnace and is gradually heated up like thermogravimetric analysis. On the other hand, if you want to try a fast pyrolysis condition, the sample cup is located at the upper part of the furnace, so where is the outside of the heating zone until the furnace temperature reaches to the desired temperature. When the furnace temperature reaches to the desired temperature, the sample cup is dropped into the furnace. So thus, the micro furnace type PYGC allows both rapid and slow heating, and broad temperatures are available. So the pyrolysis products are directly introduced into GC column, so we can skip the process of pyrolysis products collection. So pyrolysis gas chromatography can be applied to wider areas of analytical targets than other analytical techniques, including gases, liquids, solids together with cross-linked polymeric materials, so which is solvent insoluble. So this feature is vastly different from other analytical techniques such as liquid chromatography and gas chromatography. Okay, so and as many of you might know, pyrolyzer GC is available for identification of pyrolysates by employing a separation column, which is called PYGCMS method. Also, when you set lower temperatures than polymer degradation, organic additives in the polymer can be analyzed by GCMS without influence of polymer pyrolysate, so which is called thermal desorption GCMS method. So when you employ a deactivated column, so you can conduct in-situ monitoring of the evolved gas. So these are conventional ways of use of pyrolyzer GCMS. So that today's first topic is the use of pyrolyzer GCMS under oxidative environment. Okay, so thermal decomposition of polymeric materials in an oxidative atmosphere, so like air, is applied for the development of high heat resistant polymers and prediction of the lifetime of a given material. Also, investigation of the thermo-oxidative degradation characteristics of polymeric material is important to understand the emission behavior of the undesired compounds such as halogen, nitrogen, and sulfur containing molecules. However, adding air to the carrier gas is problematic in the presence of nitrogen, so M over Z value 28, and oxygen M over Z value 32, so which decrease the ionization efficiency in the electroionization mass spectrometer. Also, adding oxygen in the carrier gas leads to unacceptable decrease in the lifetime of the detector filament of mass detector, so due to the rapid oxidation of the filament. So to overcome those issues, the Frontier Laboratory developed a new PYGCMS system, so which has additional gas port here at the junction where the pyrolyzer interfaces with the GC oven. So the additional gas port allows adding helium gas to the flowing of the evolved gases from the pyrolyzer. So in essence, the concentration of nitrogen and oxygen in the carrier gas is reduced by additional helium before it reaches the ionization chamber of the mass detector. So minimizing the quenching of the ionization and associated decrease in signal to noise ratio. So the upper and lower figures shows the before and after adding the helium gas to the flowing gas from flowing gas from pyrolyzer. So you can clearly see the sharp peaks under air atmosphere. So of course, by changing the type of column, so you can identify the some oxidative degradation products generated from the pyrolyzer. So as well as the EGA-MS method, additional helium must be supplied into the gases generated from the pyrolyzer to prevent the damage of the MS filament. So during the thermal degradation, the oven temperature must be set to lower temperatures to prevent deterioration of the stationary phase of the column. The degradation product should be trapped by cryotrap during the thermal oxidative degradation, and then the carrier gas is switched to helium for the subsequent GCMS analysis of the products. So this is one example of the analytical condition. Okay, so I investigated thermal and thermal oxidative degradation characteristics of sulfur-containing super engineering plastics. So today I show you the results of polyethersulfone. So now you can see the chromatograms and EGA curves obtained by thermal degradation and thermal oxidative degradation of polyethersulfone. So sulfur dioxide, benzene, phenol, diphenyl ether, dibenzofran were detected as main pyrolysates under helium atmosphere. So not significant, but thiophenol was only detected under helium atmosphere. So on the other hand, in the presence of air, carbon dioxide and benzoquinone were newly identified. I'm sorry. Okay, so also we confirmed that the different product emission behavior under helium and air. So we clearly identified a combustion reaction of carbon over 500 degrees under air resulted in water and carbon dioxide emission. So since I have not studied the discussion of degradation mechanism yet, so I cannot explain each behavior, but I'm sure that the modified PYGCMS and EGA-MS approaches are promising techniques to understand some oxidative degradation behavior of polymers. Okay, so on the other hand, so we should not forget that thermal reaction occurs without weight loss. So this is TG curves of thermal and thermal oxidative degradation of polyethersulfone. So we cannot identify clear weight loss at 400 degrees under air, below 400 degrees from the TG curves, but oxygen content in the thermal treated polyethersulfone at 400 degrees under air was apparently increased. So this is the result of elemental analysis. So this suggests that thermal oxidative reaction was progressed below 400 degrees. So I also took pictures of polyethersulfone at different temperatures and atmospheres. So PES started melting over 250 degrees and completely melted by 400 degrees Celsius. So you can confirm a bubble formation and blackening at 500 degrees. So there is no apparent difference between pyrolysis and some oxidative degradation by 500 degrees, while carbonaceous char combustion was observed over 600 degrees under air atmosphere. And finally, no visible char was remained under air atmosphere at 950 degrees. So as a novel approach to investigate the thermal and some oxidative reaction behavior below 400 degrees, I tried to investigate radical behaviors during thermal treatment by employing ESR spectrometer equipped with a high temperature heating unit, so which was invented by JEOL company, Japan, JEOL resonance company. And samples were sealed with argon or air in the cloth cell for conducting thermal degradation or some oxidative degradation, respectively. The tube was then inserted into the ESR apparatus and heated to the desired temperature by heated air. A temperature sensor was located immediately below the sample tube, and this is the analytical condition. So the observed spin concentration in the presence and absence of oxygen revealed that spin concentration under air atmosphere was slightly higher than that in the absence of oxygen. So this ensured that chemical reaction was progressed at the non-weight loss region. So it should be noted that spin concentration under 300 degrees was non-detectable. So the thermal reaction mainly started over 350 degrees, and oxygen enhanced the formation of radicals. The G value, so which is dimensionless quantity that characterizes the magnetic moment and angular moment of an atom, was decreased with increasing temperature. Also, the G value at 350 degrees under air was slightly higher than that under pyrolytic condition. The higher G value suggests the presence of oxygen-containing radical species, whereas the lower G value indicates the presence of carbon-centered radical species. So thus, the novel high-temperature ESR allowed us to evaluate the in-situ behavior of pyrolytically or some oxidatively produced radicals at high temperatures. So since this is an ongoing project, we have not achieved the elucidation of the thermal or some oxidative degradation mechanism of this polymer. However, we have tested the combined PYGCMS, EGA-MS, and high temperature ESR approaches under air atmosphere to the several types of super engineering plastics. And we have confirmed that so this combined approach is a promising way to evaluate some oxidative degradation behavior of a wide variety of polymers. So let me move on to the next topic regarding the investigation of UV deterioration behavior of ethylene vinyl acetate, EVA. Okay. So the deterioration of the ethylene vinyl acetate EVA encapsulant under prolonged exposure to sunlight causes its discoloration, delamination, and corrosion, which are known to be the principal causes of loss in power generation. So these phenomena are commonly observed in PV modules used for 20, 30 years. So these are generally detected by visual and electroluminescence inspections, and the reduced transparency and short circuit current are evaluated by transmittance and IV curve measurements, respectively. So my current work is the investigation of the deterioration behavior of EVA encapsulant during UV irradiation. So understanding UV deterioration mechanism is important to evaluate or predict the deterioration level of EVA encapsulant. So firstly, the samples of 2 mm diameter were collected from the commercial encapsulant seed for PV modules using a micro puncher. and then the 18 films of 2 mm diameter were placed in the multi-sample or micro UV irradiator, which is developed by Frontier Laboratories. And the samples underwent UV accelerated deterioration at 6 degrees for 168 hours. The UV source has a wave number from 280 nanometer to 450 nanometer with the intensity of 500 watt per square meter. Okay, so the digital microscope and SEM images of the EVA encapsulant are shown here. So following the UV deterioration, the discoloration was observed. The SEM images of the UV deteriorated EVA encapsulant showed cracks and bubbles, so suggesting the formation of gaseous products during the UV irradiation. And the oxygen content of the UV deteriorated samples prepared at different UV irradiation intensity revealed that oxygen content is increased with aging duration. The absorbance attributed to CO or double bond stretching at this region derived from aliphatic ketones in the EVA encapsulant increased with the duration of UV irradiation. In addition, the gradual enlargement of the broad bands in this region, so which is the lactone CO double bond stretching, and also so this results providing the evidence for the formation of ketone and lactone compounds in the EVA, and the absorbance attributed to ketonic CO double stretching of this region increased further under the UV irradiation than that of lactone, so suggesting the preferential formation of ketones by UV irradiation. So furthermore, the UV deteriorated EVA encapsulants were analyzed by EGA-MS and PYGCMS methods to predict the structure of the aged EVA encapsulant from the pyrolysis characteristics. For EGA-MS analysis, the fresh and aged EVA encapsulants were decomposed by heating from 50 to 900 degrees at a rate of 10 degrees per minute. The ultra-alloy deactivated metal capillary tube, so which is called UA-DTM column, was employed, and helium was used as the carrier gas. The pyrolysates were introduced directly into the MS chamber. The GC oven temperature was set at 300 degrees. And for PYGCMS analysis, the fresh and aged EVA samples were pyrolyzed in the reactor furnace at 370 degrees for 40 minutes, so which principally decomposed the vinyl acetate unit. An ultra-alloy capillary column, so UA5, was employed, and helium was used as the carrier gas. The pyrolysis products were trapped by the cryotrap at first until the reaction was completed, and thereafter the cryotrap was removed and the pyrolysates were analyzed by GCMS. Okay, so the pyrolysate emitting behavior of the fresh and aged EVA encapsulant samples was studied using EGA-MS methods. The total ion chromatograms of the fresh and aged EVA encapsulant are summarized in the left figure. So two-step gas emission at approximately 350 and 450 degrees was observed from the fresh EVA encapsulant, which corresponds to the pyrolysis of vinyl acetate unit and ethylene unit, respectively. So for comparison, TG curves of the same samples are summarized in the right figure. the fresh sample also shows the clear two-step weight loss. The peak stop temperatures of the TIC, total ion chromatogram, slightly reduced as the UV irradiation duration increased. So particularly for the decomposition of ethylene unit, so resulting in about 10 degree for the EVA encapsulant following aging for 168 hours. The peak shape was clearly broadened by increase in UV irradiation duration, suggesting that ethylene units having a variety of chain lengths were produced following the UV irradiation. Okay, then the fresh and aged EVA encapsulant were pyrolyzed at 370 degrees using PYGCMS. The resulting pyrograms are summarized here, and the summary of the peak entries and chemical structures of the pyrolysates from PYGC analysis is provided in this table. So the pyrolysis of the fresh encapsulant mainly produced acetic acid with traces of water, acetone, and 2-oxopropyl acetate. So this one. So actually, which could be the product of a secondary reaction between acetic acid and acetone, which could be and aliphatic hydrocarbons derived from the polyethylene unit. So this result suggests that the selected pyrolysis temperature could mainly decompose the vinyl acetate unit. And then the pyrograms of the aged EVA encapsulant were drastically different from those of fresh EVA encapsulant, and included acetic acid, carbon dioxide, water, toluene, and ketones, and a wide variety of lactones and anhydrides. In addition, the aged samples produced aliphatic carboxylic acids, so this one. So evidently, PYGCMS can identify a wide variety of oxygen-containing compounds that are derived from the oxidative units in EVA. The production of ketones and lactones is consistent with the FTIR results. And furthermore, the gases evolved during UV irradiation were identified using micro UV irradiator combined with PYGCMS. So it is called UV PYGCMS, so which was also invented by Frontier Laboratories. So this system facilitates the UV irradiation of the samples inside the pyrolyzer at the desired temperatures and gas flow rates, and the subsequent analysis of the deteriorated samples by PYGCMS or EGA-MS. So furthermore, it facilitates the simultaneous UV irradiation of the samples in the pyrolyzer, and the in-situ analysis of the gases evolved during UV irradiation using GCMS. So in this work, I employed this system to identify the gases evolved during UV irradiation of EVA encapsulant. Okay, so the EVA encapsulant was rapidly aged by the micro UV irradiator combined with a pyrolyzer, and the volatiles generated during irradiation were directly analyzed by combined GCMS. So the MS chromatograms of the volatiles generated during 1, 3, and 6 hours long UV irradiation runs of the encapsulant are summarized in this figure. The generation of water, carbon dioxide, acetone, and acetic acid was observed in the early stages of UV irradiation, and the abundance of acetic acid suggests that the major component of this reaction was the degradation of the vinyl acetate unit. In addition, the generation of aliphatic hydrocarbons was observed, and the PE unit was degraded. The number of peaks detected increased with progress of aging, owing to the progress of complex EVA deterioration. Following 6 hours hour of UV irradiation, gamma butyrolactone and succinic anhydride were identified from the EVA encapsulant. So the suggested thermo-oxidative deterioration pathways by the contributions of the PYGCMS, UV-PYGCMS, and the conventional analysis are summarized here. So, and I'd like to skip the details today, but based on the combination analysis, so we can suggest the degradation mechanism, the thermo-oxidative degradation mechanism here. So this is also, so this work demonstrated the usefulness of PYGCMS and UV-PYGCMS approaches for evaluating the photooxidation behavior of the EVA encapsulant. And the final topic, so let me briefly talk about our new approach, pyrolysis, direct gas phase, derivatization-GC for online monitoring of reactive pyrolysates. So although PYGC allows rapid screening of pyrolysis conditions and pyrolysates, so we must understand the limitation of pyrolysis gas chromatography. So as Dr. Kartik has already mentioned, as an example of drawback, so GC doesn't allow detection of high boiling point compounds. So PET is a good example. So pyrolysis of PET produces terephthalic acid. The boiling point of it is around 400 degrees. So the temperature of the injection pods and column oven are often set below 350 degrees to prevent a secondary cracking in the injection pods and also decomposition of stationary phase in the column. So this pyrogram was obtained by PET pyrolysis at 500 degrees in my laboratory. So there are many carboxyl and vinyl ester compounds produced by PET pyrolysis. The carboxyl compounds cause for deterioration of chromatogram shape. In addition, there is no terephthalic acid peak in the chromatogram. So thus high boiling point compounds are not detected. So as a method to analyze polyesters by pyrolysis-gas chromatography, so reactive pyrolysis-GC technique, especially a thermally assisted hydrolysis and methylation by using tetramethyl ammonium hydroxide is often conducted in analytical pyrolysis field. So Professor Otani and Professor Ishida's group evaluated soil burial degradation behavior of this polymer, which is a biodegradable polymer. So based on the change of monomer composition during the soil burial degradation. The monomer composition was determined by the reactive PYGC technique. So in this work, sample cup containing 30 microgram of the polymer film samples and 5 microliter of TMAH solution, and was dropped. The mixture was dropped into the heated center of a pyrolyzer maintained at 400 degrees under helium carrier gas flow. The polymer chains are hydrolyzed selectively at ester linkages to form their methylated monomers listed in this table and the chromatogram. The monomer composition was determined by the amount of methylated monomers employing an FID detector. So this work is a good example of analytical pyrolysis and overcoming the difficulty of polyester analysis using PYGC. But it should be noted that so this method is not a suitable way to analyze pyrolysis reaction behavior. So reactive pyrolysis simultaneously conducts the derivatization and polymer pyrolysis in the sample cup. So therefore, the true pyrolysis reaction is limited by coexisting derivatization reactions, preventing mechanistic online pyrolysis studies. So the reactive pyrolysis is generally available for the characterization of polymer composition and microstructures. So in this work, to achieve online monitoring of high volume compounds or highly reactive pyrolysates, we have developed pyrolysis gas phase derivatization GCMS, so which is called PYGPD-GCMS method, by employing a tandem microreactor, so which has two convective heating devices. A tandem microreactor is generally employed for rapid catalytic screening, but was here specifically used for the pyrolysis of polymers with evaporation of substrates in the first microreactor and subsequent derivatization in the second microreactor. So for the present, for this work, the second microreactor was modified, allowing the direct injection of derivatization reagents and conducting of the gas phase derivatization in the second microreactor. So in this system, polymer pyrolysis independently progress in the first reactor, and the only target compounds are derivatized in the second reactor. So it allows an analysis of pyrolysis reaction producing undesirable compounds for conventional pyrolysis gas chromatography. So to reveal the potential of this method, the gas phase trifluoroacetylation of MDA, so which is one of the most major pyrolysates from polyurethanes, was tested using MB-TFA as a reagent. As I explained before, the conventional reactive pyrolysis method decomposes polymers in the presence of derivatization reagent. Therefore, the true pyrolysis reaction is limited by coexisting derivatization reactions, so preventing mechanistic online pyrolysis studies. Okay, so let me explain why MDA is problematic during pyrolysis of polyurethane using a conventional PYGC. So MDI, MDA, and MAI are major pyrolysates from MDI-based polyurethane. So when these compounds are produced and introduced into the column at the same time, they polymerize in the GC column and causes for broad-tailed peaks. So please see these pictures obtained by offline pyrolysis test. So you can see yellowish polyurea deposition on the reactor wall. Thus, prevention of the polymerization during PYGC analysis is strongly desired. So we tested polyurethane pyrolysis in the first chamber and the subsequent gas phase derivatization of MDA in the second chamber. So briefly, the first microreactor was heated to 450 degrees for rapid pyrolysis of polyurethane, and the second microreactor was kept at 400 degrees under helium gas flow, and MB-TFA was continuously injected into the second microreactor, controlled by a micro syringe pump. And after obtaining stable MB-TFA injection, the sample cup filled with polyurethane was dropped into the first microreactor. The volatilized pyrolysates were transferred into the second microreactor using helium as carrier gas, and where MDA and MAI reacted with MB-TFA. The pyrolysates and derivatized compounds were directly introduced into GCMS. So here are chromatograms obtained from conventional PYGCMS technique and developed technique are compared here. In the conventional PYGCMS method, broad peaks of MDA and MAI are observed and not well separated. On the other hand, the trifluoroacetylation MDA and MAI are successfully observed, and the peak broadening is substantially improved by the developed method. Thus, the developed technique prevented the undesired reaction between isocyanates and amines, resulting in a GCMS chromatogram closer to that of the true pyrolysate distribution. So we believe that this methodology can potentially be applied to other combinations of polymer and derivatization reactions, enabling a more in-depth characterization of polymers, including biomass and their highly reactive pyrolysates that cannot be sufficiently analyzed by conventional PYGCMS analysis. Okay, so let me conclude today's talk. So in this webinar, I introduced investigation of thermo-oxidative degradation behavior of polyethersulfone as a super engineering plastic using a modified PYGCMS system and the heating unit combined ESR system, and investigation of photo-oxidation behavior of EVA encapsulant using micro UV combined PYGCMS system, and pyrolysis direct gas phase derivatization-GC method for online analysis of pyrolysates using modified tandem microreactor GCMS system. So I'm sure that the pyrolyzer gas chromatograph system has significant future expandability and is a promising technique for investigating polymer degradation behavior and also characterization of polymer structure. So that's all. Thank you very much for your attention.
Thank you, Dr. Shogo-san. Now, guys, it's a time for the Q&A session. So if you have any questions to Dr. Shogo-san on his presentation, please post questions in the question box and we will address them now. Feel free to post your questions. I already received a number of questions. We get started with it. Let me share my screen. Okay. Dr. Karthik, you are ready for the Q&A session?
Yes.
And also Dr. Shogo-san? Okay, I'm going to post the questions one by one. Yeah, I'd like to answer them.
Yeah, so yeah, I think it is different in terms of the schematic. Okay, in EGA-MS, you have to use a transfer line, which is not required when we do with our microfurnace technology. It is going directly to the GC inlet. That is one. The second one is in TGA, you have to take a larger sample, and that is a limiting factor on conductivity. That means we have a data that shows there is always a shift in this big max temperature, which actually we can show some value addition when we use EGA-MS versus the TGA-MS.
Dr. Karthik, can you check your audio system a little bit? There is air blow, I guess. You hear the disturbance.
Yeah, okay. Sorry about that. Yeah. Okay. Do you want me to repeat?
Yeah, it'll be nice if you can repeat it again. Thank you.
Yeah. So actually, there is a difference only in terms of the schematic, because in TGA-MS you have to use a transfer line. So whenever you have a transfer line, then there are always possible for some cold spots. This is one kind of difference you will see between the TGA-MS versus the EGA-MS. And second thing is, in TGA, you are taking a 5 milligram sample, whereas in our EGA, you are taking only 0.1 milligram sample. That makes big difference in terms of the actual half peak height temperature, you know. So we have a data that shows there is a big difference of 5 to 10 degrees between TGA versus the EGA data. And that means you will have more kind of precise information in terms of this degradation mechanism with EGA-MS data compared to the TGA-MS data. Thank you.
We have a number of questions, so you try to address them as quickly as possible. Yeah.
Okay, so actually we don't really talk about the mass range. Generally, we go by the split ratio. So you can increase the split ratio when you think that the concentration is high or you are using a bigger sample size. Okay, generally, it's very difficult to answer in a generic way, because if we have to see what is your analysis, the analytical condition, because additives generally should come before the flash pyrolysis temperature. First question I may ask, have you used the EGA to set your thermal desorption and pyrolysis temperature? So I think you may have to drop an email with more details, then we can really interact on that.
Stand by. Let me.
Yeah, next one, please. Yeah.
Give me a second. Okay, there's a long question. So,
okay, general question not related to any of this talk. FSS library, we can use it only for unknown polymer or additive analysis as it will not give. I think, yeah, it can give the individual peak structure also, because we have another database called the Pyrolysis. Okay, we have EGA-MS database, then additives, then PYGCMS database. The fourth one is the Pyrolysis database. So that is actually for individual peak. Okay, so there are some information you can get it, but yeah, we do not have that for all polymers. Yeah, yeah, definitely. Please drop an email, then we can get more information or can do detailed discussion. Okay, you are using NIST and for matching the compounds. But actually, yeah, if you are using NIST, that will help to analyze most of the additive compounds. But for the polymer, NIST may not be able to tell you what kind of polymer. So some of the pyrolysis may give you a kind of peak, but the matching will be a difficult task. Again, yeah, we need to know more details on this data postman, like minimum area percentage. Those things, definitely they are different factors to consider. So please drop an email to me with details, then we can see how we can help. Yeah, Dr. Shogo, are you online?
Yeah, I'm here.
can you open your webcam as well?
Yeah. Do we have any inspiration techniques for environment present in water? So actually, I'm not familiar with that, but the filtration, micropore filtration would be great to recover micro-sized plastics from the water, and then you can directly put that materials into pyrolyzer, and then you can analyze the microplastics by using pyrolysis gas chromatograph system. It's okay.
Yeah, you can go to the next question.
Yep, please.
Okay, just a second. Yeah. Yeah,
so this is for okay, we can optimize at an early stage of method development, so where we can give a different reaction time and see the peak results. Okay, then this is how we optimize whenever you develop a new method. So you have to give sufficient time for your derivatization. But generally, since you are doing within the furnace, you don't need to wait too long. Yeah, Dr. Shogo, do you want to add anything here?
Yes, extending the reaction time, and also you can check the pyrograms of the products. Then you can identify.
Yeah, this actually, if you are interested looking at some of the polymers presence or some additives, you don't need to do a EGA-MS, because EGA-MS is more like a first step when you are trying to find a kind of navigation route, and it depends upon what is the objective of your analysis. Then we will recommend to consider EGA-MS as a first step. Otherwise, if you know, okay, this is what you are looking, some of the customers, they are just using the thermal desorption or flash pyrolysis because they are only looking for some targeted compounds. But if you are dealing with some unknown samples and some minute information, then EGA-MS is the first step to consider. Yeah, next please. Yeah, I think it goes in line with the EGA again, because if you are looking for some contamination analysis or failure analysis where the flash pyrolysis may miss out or show the hidden information, which we can dig out with a hard cutting method. Yeah. So to answer this in general, we consider this for deformulation type of analysis, failure or contamination analysis. Next, please. Okay, in terms of qualification, we have this F-search software that will help you to, because we have a summation of peak as part of our identification algorithm. So this is how we can differentiate the qualitative identification of different polymer rather than just looking at the individual pyrolysis. So that's why when you have this kind of mixed polymer analysis, our F-search will help you to overcome this common fragments between the polymers. Next, please. Yes, absolutely, because this is meant for polymer analysis, and microplastic is nothing but a polymer, and we believe we can really play an important role in this microplastic identification. Yeah. Dr. Shogo, do you have any, because I have not done this kind of characterization, do you have any otherwise we can like pass this for now and they can write to us to get that?
Yeah, so what is SS?
Because they have electrode deposited on a stainless steel. And they wanted to analyze this. Okay, so that means the stainless steel sample, they want to put it into our, that should be possible in principle, because yeah. So do you have like, have you done any kind of polyaniline type of samples?
Okay, so I have never tested polyaniline, but basically the aniline is has high interaction between a metal capillary column, so it's really difficult to well separate by using normal column. So in this case, you should use derivatization reaction before during the pyrolysis, and then I hope the polyaniline can be characterized.
Okay. Okay. Thanks. Yeah. That's good information for me as well. Actually, yeah, we have not like forgotten this topic, but this comes under this additive analysis, and we have application notes published, and definitely it is in one of the official method for doing phthalates and toys. Yeah. And yeah, I think also there's a suggestion to consider the cosmetic analysis, which we will consider in the future as webinar. Yeah, sorry. Okay, so again, this is where we may have to make use of the F-search and this library together. And most importantly, yeah, if you are doing a flash pyrolysis, sometimes you may have this problem. But if you know the chemistry of your polymer, then it is easier. At least if you know what is expected in your sample in terms of the additive, then it's easier. Otherwise, yes, it's a little extra work need to be done. That's why we try to consider a double shot approach where additives are like done first, then the same sample you go for the second step with the polymer. At least you don't see the same thing coming 2 times. Yeah, Dr. Shogo, do you want to add anything on that?
Yeah, so the temperature range should be separated, the thermal desorption for additive, and the temperature should be lower than polymer pyrolysis.
Yeah.
So that's the, I think, best way. Mm.
Yeah, next please. Okay, I think, can I ask Dr. Shogo to answer this one? Personally, I do not have much info on this. Otherwise, we will take this offline.
Mm-hmm. Yeah, that's very difficult question. Actually, it's hard to identify the type of low density and high density from polyethylene. But basically, the low density and high density has different branching. So that's why it might be possible to check the pyrolysate composition.
Yeah, actually, yeah, because we believe our research has got database for these three separately. But yeah, if you ask whether did we do this kind of mixer, I'm not sure. But we have a database for these three separately. So at least in terms of the matching against a reference would be possible. But if we have a mixer of these three, I really don't know how it would look like.
So yes, it might be good to test EGA analysis, the comparing with pure SVPE and the mixture. You might get some information.
Okay. Yeah. Yeah, definitely. I will ask this question back to our headquarter application team also. And yeah, if you are really keen to get some answer for this, please drop an email to either Bram or myself, and we will address this. Next, please. Okay, yeah, I think the first easy and simple answer will be GCMS. The PYGCMS is more straightforward, and MALDI, you know, like it's direct sample analysis, but you get a lot of mass spectra data, and data interpretation is going to be a challenge here because we are using a GCMS that helps you some level of separation, and you are taking small sample size and no sample preparation. So at least we will say simple approach first. Other than that, we cannot say much here. But yeah, again, we will take this question back to our headquarters. Yeah, I think Dr. Shogo, if you want to add anything, please.
Yeah, the PYGCMS is simple way, and I believe that PYGC is more excellent for characterizing microstructure of the polymer than GPC MALDI method. So PYGC is more simple.
Yeah, so GPC maybe for the macrostructure things. Yeah.
Yep.
Okay. Yeah. Next one, please. Okay, I hope you got some answer from Dr. Shogo's presentation. And yeah, I think we have this carrier gas selector. Okay, that will help you to really take care of this. Yeah. Yeah, Dr. Shogo, please add any further kind of comments from your side in terms of the configuration.
So the actually modification is very simple. You just add the additional helium flow between pyrolyzer and injection port of GC, and you can directly introduce air into the micro pyrolyzer without modification. So we must dilute the gas from the pyrolyzer before injecting to GC. So that's very simple. So it's okay.
Yeah. Okay. Next question, please. Okay, generally the natural rubber and synthetic rubber, we have this composition analysis technical note, and we have shown the reproducibility of the relative standard deviation is less than 3%. So you can refer to our technical note from our website, or you can drop your email that we will share that information. Yeah, the accuracy is good. Yeah. I think we are not sure about the question exactly under this inorganic filler. If it is purely inorganic material, definitely this cannot be used. But if you use some filler like additives within your inorganic filler, then it would be possible. Yeah. Dr. Shogo, do you get any details from this question? So
yeah, so you can check the weight of sample cup before and after pyrolysis, and then so you can assume the amount of inorganic filler in the material. So that's I often use this method.
Okay, yeah. So or sometimes you just have to use some of the TGA data and this together. Yeah.
Mm-hmm.
Yes, I think we can use normal PYGCMS for natural rubber analysis. Yes, next one.
And, those are the questions we have now. Thank you,
Okay.
Dr. Karthik, Dr. Shogo, and okay. So we're going to end the webinar. If anybody have any questions, you can still post the questions, and we'll pass these questions to the Dr. Karthik as well as the Dr. Shogo-san, so they can respond to you as soon as possible. Yeah. Before we end the webinar, I'd like to invite Dr. Shogo-san to share a few words to the audience, and after that, Dr. Karthik. Yeah.
Okay.
Would you like to share?
Okay.
Yeah.
So thank you very much for giving a great opportunity to talk today. And so again, I'm sure that the Pyrolysis-GC apparatus is a promising way to characterize polymer structure and polymer composition. The hopes that the further development of Pyrolysis-GC systems and researches in this field. So thank you very much.
Okay, yeah. So again, I would like to thank Dr. Shogo first for accepting our invitation to be a speaker for this webinar. His actually contribution really added value to today's webinar, and you all will agree with me on that. Some of the latest research what he has done has been shared here. And I also would like to thank Mr. Param for facilitating this webinar. And to the audience, I believe at least you have got some useful information and you would have come to this webinar with some expectation. We hope we have met your expectation to some extent, and maybe we are not actually, we have not covered the topic that you wanted to hear. If anything that you felt so, please drop an email. At least we will try to address that through email or over a call separately. Again, I thank all participants for taking your time today and at least sitting with us to know what Frontier Lab microfurnace pyrolysis system can offer for your day-to-day work. And thanks again.
Okay. Thank you, Dr. Shogo-san, Dr. Karthik, for joining and this webinar and making the presentation. I'm sure that you find it useful. And I'd like to thank all the audience for joining this webinar today. And if somebody is missing this webinar, this is available in record format. We'll be announcing shortly with the different schedules in the different time zones. So please check our website, researchandinnovationwebinar.com. I'd like to convey my sincere thanks to Dr. Karthik for initiating this webinar and the support by the Frontier Laboratories from Japan. Thank you all the team. Appreciate the support. If you have any comments on this webinar, you're always welcome to share your suggestions, feedback, and any comments on this and the topic, as well as any other future webinars that you're interested to learn from us. Please check our website, researchandinnovations-webinars.com. Thank you all. Bye-bye for now.
Okay, bye-bye.
Thank you.